Rockmore has a rather long title. John G. Kemeny Parents, Professor of Mathematics, Department Chair, and Professor of Computer Science. He is at Dartmouth College. He's a former Sigma Xi Distinguished Lecturer. And in addition to his book, Stalking the Riemann Hypothesis, which is, for math books, a bestseller, you might say. He has also published over 50 papers in the math and computer science area. So without further ado, I'd like to bring forward Daniel.
Okay, thanks so much for the invitation. Having a nice day. I don't even know if for a math book it's a bestseller, but anyway, it was an experience to write one anyway. So I had this interview a couple of days ago by Frank Gray in the Gazette, right? And so Frank was really doing his best for the first 20 minutes to not ask me, why the hell is anybody studying this problem? But finally he couldn't help himself, and that was just what he asked me. He kept sort of phrasing it as the man on the street. So I suppose it must depend on what street you walk on. For example, if you're in Princeton, I keep running into mathematicians if I'm in Princeton or in Cambridge. So it just depends on what street you're running on if you have to justify working on a problem like this. But at any rate, he did sort of leave me very attuned to that question, and so I'll try to treat that at different places in the talk. So the title of the talk is Stalking the Riemann Hypothesis, as is the title of my book on this thing called the Riemann hypothesis, and it's an old problem about prime numbers. But before we get there, hopefully, let me see what the next. Okay, great. No, we're in good shape. Okay, so the Riemann hypothesis is one of the so-called million-dollar math problems. In 2000, the Clay Institute named 7 problems that it felt were the most important problems for mathematicians to try to treat. And if they could solve them, settle them, they would get $1 million per problem. And this was big news because you rarely get $1 million for solving a math problem. You might get a headache, but you rarely get $1 million, at least directly. And so they listed these 7 problems. One of them, the Poincaré conjecture, you may have been reading in various newspapers, magazines, appears to have been settled. I would say it has been settled. It's about an area, whoops, better treat that. It's in an area of mathematics called topology, which is the mathematics of shape, roughly speaking. A second problem, which has not been settled, is P equals NP, which is an area of mathematics more related to computer science called computational complexity. And let me list the other 6 before we get there. So the Hodge conjecture, Birch and Swinnerton Dyer conjecture, Navier-Stokes, the problem of really finding a sensible way to represent the phenomenon of turbulence mathematically, and a problem in mathematical physics about something called Yang-Mills theory, so the mass gap conjecture. And finally, or maybe it should have been first, depending on how you list them, this thing called the Riemann hypothesis. And so, I don't know, you could argue about which one's the most important one. I think a lot of people, certainly all the number theorists, would argue that it's this last one, this 150-year-old problem called the Riemann hypothesis, which is really the one that mathematicians care the most about settling. So, now, so why does anybody care about these things? So I have a few PSAs throughout, public service announcements, not your prostate level. So let me say something about pure research, which is what Frank was getting at in this article. So I stole a couple of cartoons here and there, several from Sidney Harris. The beauty of this is that it's of only theoretical importance, and there's no way it can be of any practical use whatever, the guy at the board is saying. Now, the fact is that that's a pretty difficult thing to be sure of in pure research. So it's totally a privilege to be allowed to just follow your thoughts, see a hard problem and work on it, and with absolutely no care at all about what it does. That said, or what it might be good for. That said, history shows that it's a lot of these walks in the park. I'll tell you about one walk in the park in a moment, that actually, centuries later have payoffs that nobody anticipated. And this is the importance of funding basic research, research that just sort of thinks about fundamental questions without thinking about the end of the road use. So one of my favorite examples is this, something called the Bridges of Königsberg problem. Euler, famous Swiss mathematician, we'll meet him a little later in the story of the Riemann hypothesis, but there was a system of bridges in this town of Königsberg, and there was this river that ran through the town, the river Pregel, and this island there is the island of Kniephof. I'm sure I mispronounced everything. And there were 7 bridges that connected the island in the middle to the mainland. And the townspeople liked the brain teaser of could you make a path which used each bridge exactly once? Okay? So it's a nice little brain teaser, something maybe to do on a Sunday afternoon if you're so inclined. And the fact is that, many people I'm sure solved this before. Euler solved it, but the point of the way Euler solved it was that he turned it into a very serious math problem. If you had a system of vertices and edges, so he took this real-world situation, created an abstract model of it, and asked under what conditions could you traverse such a system in a way in which you would only use each edge exactly once. Okay? So that sounds like an interesting sort of parlor game. Euler turns it into a math problem and creates a subject called graph theory, okay, which Mark is an expert in, as it turns out. And Lowell. So, these guys were certainly not thinking of power grids. They weren't thinking of the internet. They weren't thinking of social networks. But the fact is that for hundreds of years, people studied graph theory. And today, we're witnessing the payoffs in that intellectual exercise. So, PSA number 1. Follow what's interesting, and centuries later, it may pay off. Okay, so that's not the problem that we're interested in here today. We're interested in the problem about numbers. Okay, and a famous quote by Kronecker, God created the integers and all else is the work of man. So let's get to work. We'll start off simply, the natural numbers. I like Wayne Thiebaud. Numbers are, if you like, man's first real abstraction. So you see instances of 1 thing, 2 things, 3 things, 4 things, 5 things, and you create some sort of common understanding of all things that are 5, and you call that thing 5. And you may create some sort of canonical object, whether it's 5 cakes or 5 hot dogs, to which everything that is 5 might refer. And that's really a first abstract leap. Okay, so, and the thing that we're going to be talking about are numbers. Okay, this very basic notion of abstraction. Now, once you start to think about numbers, these natural numbers, okay, natural in an honest sense, you begin to discover that some numbers are different from other numbers in very fundamental ways. So you could start off with the number 12, and you might have 12 baseballs, and what you notice with those 12 baseballs is that you could break them up into 3 groups of 4. Okay, so that's a certain kind of number. And you might ask yourself, can I take any collection of objects and always break it up into some sub-collection of objects such that those 2, 3, or however many collections they are, all have the same number of objects, except for the sort of trivial case where you take subsets where everything has 1 object in them. And it turns out that you can't. For example, if you take 5 baseballs, okay, well, if you could take 1 and then have, that should be 4 things over there, or you could have 2 things. You can if you cheat. You can almost always solve a math problem if you restate it, ultimately. Or you could take 2 and 3. Okay, but you can't get 2 things that have the same size, or 3 things that have the same size, and so on and so forth. So these things that can't be divided, well, things that can be chopped up are sensibly called composite. They can be composed of smaller things in the way in which I want to compose them. All the subsets have to have an equal size. Okay? Or there are these other kinds of numbers that you can't break up, and we're going to call them prime in the sense of primal. They can't be decomposed any further. Okay? So our 2 basic kinds of numbers, composite and prime. So the primes, by definition, then they're the natural numbers that can only be evenly divided by themselves and 1. Okay, that was exactly that clump of 5 baseballs. And so we see some examples here. 2 is a prime, 3 is a prime, 5 is a prime, 7 is a prime. They get bigger and bigger. Actually, I was observing a very long email exchange on some other project with 2 very famous mathematicians arguing about whether or not 1 is a prime. So I'll leave you for that in your, the punch conversation over there. But at any rate, for me, 1 is not a prime. So here are some examples, and they keep getting bigger and bigger and bigger. And there are more. There are many more, infinitely more, as we'll see. And the primes are generally referred to as the multiplicative atoms. And the reason for this kind of terminology is that any number can be broken up into a product of prime numbers, has a prime factorization. And so-called fundamental theorem of arithmetic, and it's been known at least since the time of Euclid, in fact, that there's a unique way to decompose any number as a product of primes. So again, thinking back to that clump of baseballs, you could break it up into some initial collection of baseballs, each of which had the same size, and then you could take each of those collections and break them up further and further and further and so on and so forth. Okay. And these primes that divided are called its prime factors. So here's some examples of some prime factorizations. Okay, the digits of pi are good for lots of things, including examples. Even one of them turns out to be a prime, and you could go on and on and on and do this. But so again, just the notion of a prime factorization, and the primes has really the basic ingredients of creating numbers. Okay, just as molecules are created out of atoms, not quite uniquely, but numbers in this multiplicative sense are created out of primes, and those are the basic substrate. So, natural question to ask: how many primes are there? Okay, and the Greeks asked this question, and again, some of you may be scientists from other disciplines, and it's a totally natural thing to do as a scientific discipline to identify something and then begin to try to understand the phenomenon that you've identified. And the first question you might ask is, how many kinds of these things are there? Okay, whether they be atoms or numbers. Now, it turns out there are an infinite number of primes. That list that I had there goes on and on forever. And it's one of the most beautiful proofs in mathematics, and I think this is the only proof in this lecture, so I always like to do this one, at least to give the idea. So here's the idea. Okay, and again, the goal is to show that there are an infinite number of primes. So we do the following proof gambit, if you like. Suppose that there are only a finite number. So in particular, suppose that the only primes that existed were 2, 3, 5, 7, 11, and 13. Okay, those are the only primes in the books. Now I can make up a new number out of those basic ingredients. I can multiply together all the primes that I've listed, 2 times 3 times 5 times 7 times 11 times 13, and then add 1. Okay, perfectly good number, which turns out to be 30,031. Now, we know, because it's a number, that it has a prime factorization. The primes are these basic atoms, right? So let's investigate the prime factorization of this number that I just cooked up. Well, if the only primes were 2, 3, 5, 7, 11, and 13, then it must be that each of those numbers has to divide this number here, right? So let's see what happens. Well, if we divide it by 2, okay, you get a remainder of 1. If you divide it by 3, you get a remainder of 1. If you divide it by 5, you get a remainder of 1. And so on and so forth. You can see that perhaps fairly quickly if you see, when you look at the factorization up there and you divide each of those numbers into it, then you're basically just lopping off that factor inside the parentheses, but you're always leaving off the 1 at the end. Okay? So dividing by any of the primes in the original list gives me a remainder of 1. So that must mean that there has to be some prime factor which is not in the list that I wrote down. Okay, I mean, I haven't constructed it for you, but it can't be one of these because none of these numbers divide it evenly. Okay, so that would be true regardless of what finite collection of primes I started with, right? They could be the first few consecutive ones. They could be some random assortment of them, but whatever it is, if I have a finite collection of them and I multiply them together and add 1, then the factors of that new number must include a prime that I haven't started with in the beginning. Okay? So that's a non-constructive proof, if you like, of the infinity of primes. I haven't given you a rule to generate a new prime at every time, but I've shown you that for any finite set, there has to be another one that I missed. Okay? So an infinite number of primes, and this is Euclid's proof. He was a smart guy. So now I know I have an infinite number of primes, and now lots of questions. Okay, and again, questions just because I've identified this strange new species of thing, and I want to try to understand it better. Okay, totally natural, scientific, epistemological instinct, if you like. And the fact is that folks like to talk about the primes. I love this cartoon of the guys in the bar talking about the primes. It turns out that if you write a book related to prime numbers, you would be shocked to discover how many people want to tell you what they think about the primes. They come from everywhere, and they're related to the stars, and they're related to past lives, and besides being related to cryptography and things. But people like the primes. So here's a good question, and this is the question that we're going to be talking about. We now know there are an infinite number of primes, but can we be a little bit more precise about that notion of infinity? Okay, and yeah, so let me leave it at that, and we'll elaborate on it in a moment. Is there a pattern to the way the primes occur? Start to list them out. Is there some way to describe when we would expect the next prime to occur? Some sort of law of growth, if you like, of the primes. Okay. And the answer is yes, and that brings us to what will be the Riemann hypothesis. So that's what the Riemann hypothesis is about, saying something more precise about the way the primes grow. Okay, some law of growth for them, if you like. Yeah, I mean, so before I do this, some of you saw I showed a movie that I made earlier today, and there's a little bit in there where I talk about this. And for example, if you had just started studying the primes, you might notice that 3 is a prime, 5 is a prime, 7 is a prime. So you could say, oh, I know. Every odd number is a prime. Okay, and then you come up to 9, and 9 is 3 times 3. It's not a prime. But you've sort of started this investigation, where you begin to wonder, well, all right, 9 didn't work, but so maybe there's some other rule that would include 2, 3, 5, and 7, and now I have to jump to 11. So there's a gap from 7 to 11 of 4, but then there's a gap of 2 from 11 to 13. Then there's another gap of 4 to 17, then another gap of 2 to 19. Oh, so maybe they go 4s and 2s after that initial messing around. But, okay, well, you add 4 to 19 and you get 23, but then you add 2 to 23 and you get 25, and the game's over again. So this is the sort of thing that a mathematician would begin to puzzle about, or just, again, the guy on the street, depending on your town, right? Or the guy in this bar here, for example. So let's start to look for the primes. So the Greeks thought about this. How can we find these things that we're now calling prime numbers? So Eratosthenes, who I believe he's famous for this prime hunting algorithm that we'll talk about in a minute. I think he's also the first one to estimate the diameter of the Earth, and he got pretty close, within a couple thousand miles. So here's one way to find the primes. Okay, I could start. So suppose I want to find all the primes up to 140. Okay, I'll start in the following way. I know 2 is a prime. But now I know that anything that's a multiple of 2 can't be a prime, because by definition, 2 divides that number. So I'm going to get rid of all the multiples of 2. You see, I crossed them out there with the red lines. Okay, all those can't be primes. That means, so now having done that up to 140, I go to the first number in the list that I didn't cross out. That thing has to be a prime because it's not divisible by anything less than it. Okay, so that number happens to be 3. That's a good check. 3 is a prime. Now I go through the list and cross off any number that's a multiple of 3 that I didn't already cross off because it was a multiple of 2. Okay, I get all the way down to the end. I stop. Then I know that the next number that hasn't been crossed off yet must be a prime. Why? Because it's not divisible by anything less than it. okay, and so on and so forth. This is the sieve of Eratosthenes, okay? So now we look at these numbers that are in white, the bold-faced numbers, and again, hoping to find some kind of pattern there. Well, you're not going to find one. Not one directly, but we begin to notice some things. So first of all, there are some interesting kinds of little sub-patterns. Often we see these repeated primes that are separated by 2, 137 and 139, or 3 and 5, or 5 and 7. These are instances of things called twin primes. Talk about those for a moment later. But generally speaking, the gaps between primes seem to be getting bigger and bigger. And that makes sense, right? Because I'm doing this thing of chopping out numbers based on multiples. And so I just start chopping out more things toward the end, because there's sort of more opportunity for them to be built out of smaller things. Okay, so they seem to be getting more and more spread apart, but there are these hiccups. And that's sort of the mystery. Generally, they seem to be getting farther and farther apart, but there are these sub-sequences of, where they aren't, where they're just closer than we would expect them to be. But we're mathematicians, so we keep trying. We're interested, so we keep trying. So we begin to take some more data. Okay, again, perfectly sensible scientific gambit. There's some phenomenon that we want to understand, and we begin to look at data. So, let's see if I can get back to that. Okay, good. So I tried to use very, very little notation in this talk, but again, notation is just a way of writing less on the slide. So this graph here, okay, this what we would call a step function. Okay, the height at any point, for example, if you went up, if you could draw a line up from 20 up to where it intersects the staircase, that would tell you how many primes there are less than 20. Okay, you go up to 40, again, the part of the staircase you're on has some value over on what we would say the y-axis, the vertical axis. That's the number of primes less than 40, and so on. So it's a step function because sometimes between two numbers there are no new primes. Right? So the number of primes less than or equal to 18 is the same as the number of primes less than or equal to 17, for example. So you get a step there. Okay? So you get this jaggedy step function, okay, going up to 140, where there are about 30 some odd primes less than 140. Is that okay as a picture? It's going to be a sort of important picture. Okay, so I'm just charting the way the primes grow. And they grow in this jagged way, but the function is increasing because the number of primes less than or equal to any given point is always going to be bigger than some point beneath it, right? Bigger than or equal to. Maybe, again, one of these plateaus. Is that okay? All right. So again, looks like we're in big trouble. But what I want you to think of now is it's sort of like trying to understand, roughly, well, what's the shape of a coastline from walking along the shore? Okay, that's a pretty complicated question, all right? But if you get up on the cliff, you begin to see the outlines, and if you go up on an airplane, you do even better, and if you're orbiting the Earth, you can do an even better job of sort of seeing it as a curve of some type. So let's see if we can't at least get to the top of a cliff. So here, and the scale is, we won't get into the problems with statistics and getting the right scale to make the picture right. So number of primes less than or equal to 1,000. Okay, and now we actually begin to see some kind of structure, right? It almost looks straight, in fact. Okay. Again, a little bit of up and downness. You can see it there. And let's go one more, up in the Challenger or something. And there we go. So the number of primes less than or equal to 1,000,000. So that looks pretty much like a straight line, okay? Now we have to do a little bit of reasoning. And again, what I'm trying to get, so it's almost as if at this point you have to think, well, I've punted on the idea of being able to predict exactly when another prime is going to occur. Okay, but what I am interested in is roughly, for very big values, what will this curve line look like? Okay, can I make some statement about that, even if I can't predict precisely where the next prime is going to occur? Because that actually turns out to be basically an impossible problem. Okay, so I've already given up on that, but I'm going to do something what we hope is a little easier. So now this thing looks like a line, but it can't be a line. It can't be a line for the following reason, okay? So you know how people always talk about, nonlinear thinking, okay, a nonlinear phenomenon, what people say colloquially. Basically, what they mean is that what you get out doesn't look anything like what you put in, okay? Somebody really wasn't proceeding in a sort of push here and outcomes with the same amount of push kind of relationship. You get something totally unexpected. What that would mean for a linear phenomenon for primes would basically mean that you would expect the same number of primes roughly for every chunk along the number line. Okay, and we've already more or less argued to ourselves that that shouldn't be the case. Okay, the farther out you go, the more opportunity there is for factors, and so there should be fewer farther out, sort of in a notion of density. Okay, if you took a chunk of the number line way out by 1 billion, you would expect fewer primes than if you took the same chunk over by 100, for example. Okay, so for that reason, I don't expect something linear. So what might I expect this thing to do? Now, this, I'm hoping, this is PSA number 2, and I'm hoping, so everybody, I know if you're not a mathematician, you hate logarithms. I already know that, okay, I know that. But the fact is that you can't, the amazing thing is that you can't talk about prime numbers without talking about logarithms, or at least to mention them and then forget them in a minute. And that's just some funny, it's almost like some weird cosmic coincidence because, for example, the seismic, so seismology, the Richter scale, decibels, all these things that your senses, that measure the way in which your senses receive the world actually behave in a logarithmic way. Okay, just as an aside. So it's I'm sure that there are people, that there might be physiologists here who will tell me why there should be this connection. But at any rate, logarithms are the right scale for the senses, and it turns out that logarithms are the right scales for the prime numbers. Okay, so let me just remind you, and feel free to forget it, but if you like to have the reminder, memories of the logarithm. Okay, so here's some logarithms of base 10, okay, and the logarithm is a quite simple thing. So in base 10, the logarithm of 10 to any power is simply the power, okay, so it's just measuring the power. Now the interesting thing from our point of view is that logarithms grow very, very slowly, okay, the logarithm in base 10 of 1,000 is 3. The logarithm in base 10 of 1 billion is 9, okay, so this is a function that at 100 is equal to 2, and at 1 billion on any scale where I'd be, what direction is that? East, west, north, or south? I don't know. But wherever I am going that way, outside of the United States probably, I would hit 1 billion. And then it would equal 9, whereas here it was equal to 2. Okay, so that's a very, very slowly growing function. So one thing that I might imagine is that curve that I saw on the last page, on the last slide, it's not exactly a line, but maybe it's a line that's being modulated by something else that's very slowly growing, dividing at every point by a number that's getting big, but very, 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 very slowly, and in a slightly unpredictable and non-linear way, like maybe the logarithm, for example. So, in fact, this did occur to someone. And it occurred to someone in about the 18th century, and it was Legendre. Legendre, famous mathematician, scientist, he took a statistics course. He's famous for having originated the method of least squares. So the first thing you learn about when you're trying to fit data. And as many mathematicians were in those days, he was also an astronomer, and a lot of what he developed was in the service of astronomy, which was really the big user of mathematics for centuries. Many mathematicians had their first great results in the service of astronomy, including Gauss, who we'll get to in a second. So Legendre saw that data. He computed some data. I mean, these guys, they weren't just sitting at their desks thinking great things about prime numbers. They actually computed. They computed big tables of numbers and plotted them. And then, as would befit somebody who was trying to map where some sort of celestial object was going to be, he tried to map where was the next prime going to be. How can I get a law of the primes? So Legendre posited a rule for the growth of the primes that looked like this. Now there's some notation, but roughly what it says is that it grows like a line, but at every point I divide by something times a logarithm plus a little bit, and I don't know what that something is, A, or that little bit is, B, But Legendre, he knew how to do this least squares thing. He knew how to fit data. He said, well, I'm going to find the best values for A and B. And that's what I'm going to declare as the growth law for the primes. Okay, just again as he might extrapolate where the next place is that he would see a comet, for example. So he came up with this rule, okay? X log x plus 1 and change. Now, anybody here who's fit a little bit of data might be worrying now, okay? The primes, how many people here fit data, just out of curiosity? Anybody? Anybody? I do. If you fit any data, you know you have some finite set, right? And in this case, Legendre knows he has an infinite number of observations that he hasn't made. Okay, so there's a potential to overfit the data to the finite, relatively small set that he had, right? And so he should have been very worried, especially since he was making what we call an asymptotic law here. He was trying to predict the behavior out to infinity. Now, out to infinity, even though log x grows very slowly, if I take the logarithm of infinity, so of 10 to some huge power, I'm going to get that huge power back, right? So eventually, out to infinity, this little bit here gets swamped anyway, goes away. So Legendre should have been smart enough to get rid of that extra factor. And if he had, he would have been credited with having discovered the prime number theorem. But he didn't. He left it in there. He was a very cantankerous guy. So Legendre guessed that. Poor guy, because he was going to be surpassed by Gauss, who surpasses everybody eventually. So Gauss is, by anybody's account, the greatest mathematician of all time. As befits the prince of mathematics, and as befits the greatest mathematician of all time, as a boy, I considered the problem of how many primes. I considered the problem of how to lace up my baseball glove. But he considered the problem of how many primes there are up to a given point. And Gauss computed tables upon tables upon tables of prime numbers. Okay, as he revealed later in a letter to a former student of his. Gauss was also famous for not... Wait, is few but ripe Gauss? I can't remember. Yes, few but ripe is Gauss. So Gauss's desk was filled with unpublished manuscripts because they weren't perfect. And so in particular, he had some guess about the behavior of the primes based on these childhood number theoretic explorations. And what he discovered, so he would compute them in sort of blocks of 1,000. And in each block of 1,000, up to 1,000,000, I think, or so, he would see how many primes were in each block, what we would call the density of primes, the number of primes per 1,000. And what he noticed, he had a good eye for data, and let me say it again, he had a good eye for data. He, too, his first known result was predicting the appearance of the asteroid Ceres from data. That's what made him famous as a young astronomer, before he was famous as a mathematician. So he had this data, he looked at the data, and what he noticed is that for any number x, if you took the midpoint of those 1,000 numbers, the one in the middle, that roughly the number of primes in that chunk was 1 over the logarithm of x. In this case, it's the natural logarithm, and we won't discuss the natural logarithm, but it's roughly like the logarithm I just showed you. It has to do with e as your base. So using Gauss's data, for example, his data would show that around 1,000,000, you would expect about 1 out of every 13 numbers to be prime. Roughly, not exactly, okay, but on average, more or less. So Gauss, better with his data than Legendre, conjectured the prime number theorem. So Gauss conjectured that the primes grow, again, like a line, but at every point divide by this very, 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 very slowly growing function, the logarithm. Okay, so it barely perceptibly changes it from a line, but it does begin to sort of pull it down a little bit. From his thinking, you would conclude that the nth prime, like the 100th prime, is roughly equal in value to 100 times the logarithm of 100. Okay, you could conclude that again from his reasoning. And in fact, he had a very, very precise formula which involves an integral, but that's not important. So he had a more precise reckoning of the number of primes. And his reckoning was basically, if I know what the density of primes is all along the number line, then the way in which to figure out how many primes there are up to a certain point is basically to add those chunks, right? If I know that 1 out of every 20 in the beginning is a prime, and then 1 out of every 30 in the next chunk is a prime, and so on and so forth, if I add those all the way up to a given point, I can tell you roughly how many primes there are. And that's what's encoded in this integral. Okay, and it's a special function called lie of x. Okay, but at any rate, he had a specific formula for this asymptotic, for how this curve should look from space, so to speak. And that gave him a rough formula for the nth prime and, again, the prime counting function. So, so you can compare these two guesses. And so there's Legendre's guess, and there's Gauss's guess on the bottom. So you can see that Legendre's guess, even though there's that little change in the denominator, really starts to swamp Gauss. And in fact, so the difference, so the what's over on the right, sorry, is the is the error. Sorry, it's the error over here. So at 10 million, Legendre's error is 560. Forget about the middle guy. That's this old student of Gauss, Encke, another astronomer. And Gauss only misses by 338 in absolute value. So it's not, you know, the difference isn't big. But again, for the primes go on forever. So we could, I mean, you know, if we had enough time, we could do this table up to 100 million. And then they would really be differing quite dramatically, as you can see, okay, over there. So Gauss's guess is better. And so now there's a question. It's a better guess. Now we have an idea of what kind of theorem we should prove. What sort of result should we look to be true? Forget about doing all these experiments. Can I actually write down an argument that says that Gauss's guess, this lie of x, or at least this x over log x estimate, is true no matter how much data you give me, that I know that's the right answer? That's what I mean by writing a proof. So, so Gauss made this conjecture, and people weren't able to prove it. Okay, another hypothesis. Mathematicians call things they can't prove conjectures, or else you just don't tell anybody about them. Only famous mathematicians call things they can't prove conjectures. The rest of us figure we're just not smart enough. I mean, you know, Gauss would call it the prime number theorem. I mean, he knew it was true, even if he didn't have a proof of it. So the next actor to come in, or the next figure to come into the story is Euler. Okay, and we already met Euler as the guy walking around the bridges of Königsberg, developing graph theory. But Euler did a million different things. An incredibly broad and prolific mathematician. In fact, people are still editing his works, you know, some 300 years later. So Euler had a totally different view of the problem. So again, you know, I know as soon as you see equations, many people here want to go to sleep, but let's at least try to understand what the basic idea was. Euler wanted to understand how the primes grow. Okay, so it's a list of numbers along the number line. Okay, so Euler had this totally inverted point of view. Okay, if the primes grow very slowly, okay, meaning that there are lots of primes up to a given point, then think about doing the following thing. Taking each of those numbers, taking the reciprocals, and adding up those numbers. Okay? If I'm adding up lots and lots and lots and lots of little numbers, okay, it may be the case that either I get something which is bounded, or I get something that grows unboundedly. So for example, look at the above, what we would call an infinite series. I can walk halfway to the wall, and then halfway again. So in other words, if this is a distance 1, I go a half, then I step a quarter, an eighth, and so on. It makes sense to try to add that. At the very least, I know that if I take all those steps, it's bounded by the distance to the wall. Okay? But you could do another kind of walk, where you could walk half the distance, then a third of the distance, then a fourth of the distance, and so on. Eventually, you'd walk through the wall, if you could. And it would turn out that you would keep on walking forever. Okay, that this infinite series that I write down in the second line there, so-called harmonic series, actually grows past any bound that you can write down. Okay? And the same is true of the primes. Okay, if I take the reciprocals of the primes and I add those, that's also unbounded. And what Euler felt was that the key to how quickly this number grew would be the key to understanding how the primes grew. Okay, so looking at these infinite series. Okay, so in fact there are some implications here. So the primes, it turns out, must be denser than the squares. The squares, if you add the reciprocals of the squares, okay, the squares get big so quickly that eventually you're adding a number that's so small that it doesn't matter anymore. Okay, and that number is bounded, just like the distance from here to the wall, if I go half the way and half the way again, and so on and so forth. Whereas the primes go out to infinity. So I can conclude things about the densities of the primes relative to other kinds of numbers. Now, it turns out that the key mathematical object is some generalization of these series that I've been writing down here. It's a so-called Riemann zeta function. Now, we're actually not really going to talk about the zeta function, but I have to write it down at least once here, because it turns out to be the main thing that we're looking about. And it's exactly this thing where you consider what sum you get if you take these reciprocals and raise them to a power for an arbitrary power. But the takeaway message is that that somehow the growth of this function in one way or another is going to be related to the growth of the primes. Okay, so here comes Riemann. So I put this cartoon here, okay, because the truth is that at the heart of the Riemann hypothesis is something that's a little technical. I mean, you saw that zeta function, and you know, if you've never seen any mathematics before, that zeta function totally intimidating. Even if you've seen a lot of mathematics, that zeta function is totally intimidating. So I'm going to try to explain now the Riemann hypothesis without being a little bit more explicit in step 2. Okay? And the fact is, it's kind of a miracle, and I have to say that, so I'm not a number theorist, even though I wrote this book. I have to say that even, I mean, when you read it, and you read it, and you read it to understand it, it still feels like a miracle that there's a connection. I mean, even for somebody who's had a lot of mathematical training. So, you know, that's, I have to say, this is and again, somebody said this in my movie, you know, mathematicians, it's true of all scientists, I'm sure, but you spend most of your time feeling stupid. You know, you're trying to understand something, and generally you don't understand it. The 365 days in a year, if you have 3 good results, that means you understood something for 3 days. So if you had 3 good results, you had a pretty good year. So, you know, you really, you have to get used to failure a lot on a personal level. So you have to have a good sense of humor about yourself, I think. So yeah, don't take yourself too seriously. Okay, so the miracle maker, Riemann. Riemann, as you can see, lived barely 40 years. He wrote a very small number of papers. He only wrote 1 paper on number theory, which is the subject of the Riemann hypothesis, and it was 8 pages long. Okay, and he worked mainly in mathematical physics. In fact, most of the mathematics of general relativity, space-time geometry, all these things are Riemannian geometry, and that's, you know, at least as equally as great a legacy as this one small paper. But it's the one small paper that we're interested in. So he gave the paper at a sort of honoring ceremony of his along his scientific career, and he had to write a paper for it. And so he had this idea, all right, I have to write a paper, I'll write this paper. It's called On the Number of Primes Less Than a Given Magnitude, and that's what we've been studying. Okay, how many primes are there up to a given magnitude? Now, Riemann was guided by another subject that he knew called Fourier analysis. So again, the problem is trying to understand, remember I had that step function there. Okay, now imagine that step function, but now instead of letting it grow, let's sort of turn it on its side about 45 degrees. And so instead of getting a step function, I'm going to get some jaggedy up and down thing, right? Something like you might see on an oscilloscope, okay, or you know, EKG or something like that, okay? A wave of some sort. Now, Fourier analysis is the mathematics of waves. And so Riemann, like the thickening and thinning of the primes. Remember how we saw, you know, generally there could be these big gaps, but then there could be these hiccups of these twin primes along the way and other sorts of smaller gaps. So that's this thickening and thinning that he's referring to. He had written a paper, one of his sort of his pre-dissertation work on Fourier analysis, so he wondered, you know, could there be some analogy? Could I use the mathematics of waves to understand the mathematics of prime numbers? So just to make a little bit more clear what I'm talking about, so there's sort of basic what we would call sinusoid. okay? Basic, think of it as a pressure wave. It's you know, like a perfect A, okay? Would look like that if you could generate one. Waves have characteristics. These perfect waves do. There's an amplitude. The maximum they go either up or down relative to some rest position. There's a frequency, which is the number of waves that fit in a given slot of time, or if you like the inverse, the period, which is the length of one wave from crest to crest or trough to trough. These are perfectly periodic functions here. There's also a notion of phase, okay? I can ask where the wave starts, one of these perfect waves. This one's starting, if you like, at 0, pinned to 0. This one is starting over here at 1, okay? There are different phases, okay? Those are generally three characteristics of a wave. Fourier analysis is the mathematics that allows you to take any sort of periodic behavior, okay, and turn it into a sum of simple sinusoids, okay? So, you know, this is what's happening here. If I'm adding up a bunch of these basic waves, I'm getting a better and better and better approximation to this sawtooth here. All right, so you may need an infinite number of harmonics if you like to generate this periodic thing, but Fourier analysis tells you how to decompose any periodic behavior into a basic collection of sinusoids. It's sort of like a recipe. Given this sound, okay, I know I need a big chunk of A and a little chunk of C and so on and so forth. Okay, Fourier analysis is the mathematics that deconstructs this. So, as I said, there's this thing, the zeta function, which is the miracle that occurs in step 2. So, the zeta function, I've tried to represent the function as a machine with that canister there. So, generally speaking, a mathematical function takes as input a number or a collection of numbers and spits out another number. Okay? The zeta function is one such machine. Now, the difference is that the zeta function takes as its input complex numbers. Now, complex numbers are a particular kind of number. I'll say a little bit more about them in a second, but take my word, complex numbers are not complex, okay? They've been totally messed up by this terrible name. Complex numbers, actually, mathematicians will tell you, simplify everything. Everything in mathematics is easier with complex numbers than it is with real numbers. I should say that complex numbers are also real in the sense that complex numbers are the numbers that engineers use all the time to understand electricity and magnetism, for example. They're really, they're fundamental to engineering, they're fundamental to geometry, and they just have a lousy name. Okay? I was going to say a joke and use somebody's real name, but with some probability somebody actually has that name here, so I'm not going to do that. But it's a machine. It takes a number, spits out a number. In this case, we denote this number with the Greek letter zeta, zeta of S. Now, the miracle is that, so the miracle is, there's a sense in which it's not so miraculous that Riemann thought of using this particular machine to try to understand the prime numbers. The real sort of miracle is that the numbers that matter are the numbers that when you toss them into this machine, make the machine spit out 0. Okay, the so-called zeta zeros. Okay, these are going to be the important numbers. So, right, so again, there's this machine, the zeta function, and what Riemann figured out is that it's the numbers that when you toss them into this machine and get 0, those are going to be the numbers that tell me which waves to use to make that turned over prime number, prime less than function that I made. Okay, so he constructed this machine to tell him which waves to use. Now, the connection between the machine and the function is the miracle. And so we're all just going to have to be believers for today. Okay. So that's the miracle. So here are some of these waves, okay? So these waves, again, are indexed by these things called zeta zeros. The zeta zeros have, as we'll see, they're naturally listed in some way. Here's the first one, the second one, the third one, the fourth one, okay? And so there are these waves that are, you can sort of see the thickening and thinning somehow within them. All right. Now, that's right. Sorry, it takes the pictures, I guess, are a little big. So I hope you can see. Can you see the little step function? That's okay. So if I use the first 5 zeta zeros, to try to approximate this prime less than or equal to function there, I get not such a great approximation. If I use the first 50, I'm doing all right. If I use the first 500, that's an incredibly great fit to that jaggedy function. Okay, so this is a sort of amazing thing, right? I mean, the step function, it's a step function. It has those hard edges. You saw those waves on the previous slide, right? They're beautiful and snake-like. But if I add up enough of these things, I begin to get my step function back. Okay, so that was Riemann's amazing, again, Riemann's great insight to connect Fourier analysis, again, the mathematics of continuous wave-like media, and these discrete things, the primes. Okay. All right, and that what we saw there is something called Riemann's explicit formula, and actually it's not so important really to go over what I don't want to go over what complex numbers are, but let me skip that. There's a very scary formula, so forget about that. And the important thing is now using Riemann's count, look at how close he's getting. Okay, so this is Riemann's error using, I think, so this is for the first 500 waves, if I use that for my approximation. And up to 5 million, okay, only misses by 64, up to 4 million by 33. It's a very, very good approximation. Okay, using this sort of wave-like expansion. Okay, take a second. All right, so now, what is the Riemann hypothesis? So, there's a lot of verbiage here, so let's go down all the way to the bottom and actually turn that into an English sentence. So the takeaway message, all right, is that Riemann's hypothesis, Riemann said that, remember, to make up this expression for the primes less than function, it depended on where this magical thing called the zeta function was equal to 0. It depended on what these zeta zeros were. The take-home message is that Riemann conjectured that all those zeros had a very particular, very simple to state form. Okay, so that's a summary statement. You could say in one sentence, well, all these things that make the zeta function equal to 0 are very easy to describe. And okay, end of story. And then he said how they were very easy to describe. Now, if you want to go one sentence further, he would say they were very easy to describe, and they were complex numbers. Complex numbers actually have two parts. They're like points in the Cartesian plane. And he would tell you that they're complex numbers whose whose real part is equal to 1/2. Okay, so on the xy coordinates, their x coordinate is 1/2 and their y coordinate is whatever. But they're all on one line in the complex plane. Okay, so the simple statement is the Riemann hypothesis says that the waves that I need to make the prime counting function are very easy to describe, and I can give you that description in a sentence. The slightly more complicated one is that they're complex numbers with real part equal to 1/2. Okay, and they're on something called the critical line. Okay, that's the Riemann hypothesis. So, Riemann actually, he would have liked to pursue it, but he had other things to do. In particular, he was going to die quite soon. Not that he knew that, but his health was never great. And he looked for a while, and he did some calculations, and that's how he came up with this hypothesis. He didn't call it the Riemann hypothesis. He just said, I think the following thing is true. And that was sort of the end of it. Or said a little bit more than that. Now, okay. All right, so why do we care? Okay, so again, if you're this far and you're still interested, then you're interested in prime numbers. And the reason that you care is because if the Riemann hypothesis is true, then I get a very, very precise estimate of how many primes there are up to a particular point. Okay, and the more of those squiggly things I use, the better my approximation is. And I can tell you exactly how good that approximation is. And that's what von Koch wrote down, that there's a very good error term. Okay, and what this thing shows here is the error term going to 0, basically, by using the zeros of the zeta function as your to index your waves. But now, let me give you, if you're not so interested in primes, and and Frank wants you to care about, what we're going to use these for down the road. Let me say something about primes and their use. So you can, again, why do basic research? Because you never know. So people chasing the Riemann hypothesis, this is basic understanding about the prime numbers. Let me tell you a very simple fact about prime numbers. Okay, here's a very simple fact. Fermat's little theorem. You may have heard of Fermat because there's Fermat's last theorem. But not everybody there was Fermat's last theorem. But what about Fermat's little theorem? Fermat's little theorem is actually much more useful than Fermat's last theorem. And here's Fermat's little theorem. If p is a prime number and n is a number not divisible by p, then if I raise n to the p minus first power and divide that by p, I get a remainder of 1. Okay, so here's an example. Okay, p is 3. Then p minus 1 is 2. So I look at 1 squared, I get 1. If I divide that by 3, I have a remainder of 1. 2 squared is 4, and I divide that by 3, I get a remainder of 1. Turns out you only need to do those two to prove it for all of them. Similarly for 5. Okay, 2 to the 4th, p minus 1 is 4, I get 16, divide that by 5, remainder of 1. Okay, that's a nice pattern involving primes and numbers. Okay, very, very simple pattern. Now, 1650. No way Fermat is anticipating Amazon.com. All right? He's smart, but he's not that smart. This pure theorem, just an observation, it's a beautiful proof, something you prove in a first number theory class, is absolutely the cornerstone of modern digital security. Okay, this is it. I mean, there's some other clever ideas there, but you need this fact and some slight generalizations of this fact. Okay, and Fermat was just sort of like a local magistrate who liked math. Didn't even patent it. What was he thinking about? Okay, so, but we're interested just because we're interested in primes. So the Riemann hypothesis is stated, and now people actually have a way to try to understand this prime counting theorem. So the Riemann hypothesis is stated, and now, actually, this explicit formula that we wrote down, this way of writing down the prime number, the prime counting function in terms of these waves, is an incredible breakthrough. It allows people like Adamard and Devalet-Poussin to prove the prime number theorem. The prime number theorem still hadn't even been proved. People were still referring to it as a conjecture, Gauss's conjecture, about how the primes grow. And so these two guys almost simultaneously prove that thing for sure. And along the way, Devalet-Poussin also begins to prove some things about the zeta zeros, actually making some progress on what the pattern of the zeros is. And now along the way, so lots of people try to prove the Riemann hypothesis. I mean, it was known as a hard problem and an important problem pretty much from the time it was stated. It was one of Hilbert's landmark problems that he said had to be solved at the turn of the 20th century. So many people tried to solve it. And there were some famous missteps. Stiltjes, Dutch mathematician, I believe, related it to some kind of funny random walk. So maybe some of you have read Random Walk on Wall Street. So Stiltjes actually found some way to relate a different, slightly modified random walk to Riemann's hypothesis. He claimed in a letter, actually claimed multiple times in letters to the mathematician Hermite, that he solved the problem, but he was just about to write it down, but he had to go do his laundry. I've solved the problem, but oh, I'm so tired I can't write it down yet. I've solved the problem, but oh, I can't tell you yet because I mean, there's letter after letter like this. They're very funny to read. And did he? Didn't he? Probably not, in fact. I have managed to put this proposition beyond doubt by means of a rigorous proof. Well, history hasn't shown that. Other did they or didn't theys? So Rademacher, mathematician, mid-20th century, mainly at Penn, claimed he had a proof of the Riemann hypothesis. He wanted it to be checked by the famous mathematicians at the Institute for Advanced Study. His chairman, however, got wind of the fact that he said he had proved this result. So his chairman called up the newspapers and said, Rademacher has proved the Riemann hypothesis. There's an article in Time magazine. Poor Rademacher was so horrified. He goes down to Princeton, shows this manuscript to a mathematician who stays up all night and says, I found a mistake. So Rademacher, he used to visit Dartmouth in the summers. He had a house there, and you weren't allowed to mention the Riemann hypothesis if Rademacher was in the halls. So anyway, this is a picture from Time magazine. Right, so here's where you made your mistake, all the way at the beginning. In fact, it was all the way at the beginning. You made a very, very, it was bad assumption at the beginning. John Nash, of A Beautiful Mind fame, claimed to have solved the Riemann hypothesis. And it's a terrible story. I mean, he claimed to have solved the Riemann hypothesis. It was in a famous lecture where people first began to get an inkling of the fact, and publicly, that he had schizophrenia. And so but in fact, the ideas that he said he had for solving the Riemann hypothesis in this lecture, even though it didn't seem right, it turns out, by coincidence, are the ideas that are being used today to try to approach the Riemann hypothesis. I'll get to a close very quickly then in the following way. So by the early 70s, several people had claimed they had solved it. They had all been proved wrong. They hadn't solved it. But there was plenty of numerical evidence, for example. So these simple to describe zeros, there are an infinite number of them. Okay? And so people began to compute them. And what they were able to show by the early 70s was that the first 3.5 million of these zeta zeros were exactly as Riemann described they should be. Okay? And people had begun to actually prove some theorems about them. Okay? That, remember, they had to be a very specific form. And people like Levinson showed that, generally speaking, I can prove that some proportion of them are of the form that Riemann said they are. This isn't to say that the other ones aren't, just that I can't say anything about them. Okay? And there were analogs of the Riemann hypothesis that were being proved in different settings. So there was plenty of evidence that this thing should be true. So let me explain this, because this is where the big work these days is mainly centered around, and why there were 4 books written by it all at once in about the year 2000. And the connection comes from some crazy relationship between prime numbers and atoms, of all things. So Freeman Dyson is probably the greatest physicist to have never won a Nobel Prize. I think that's how some people refer to him. Totally outstanding scientist at the Institute for Advanced Study, mainly known for his work on fundamental particles, but actually grew up as a number theorist. He wanted to be a number theorist. There's a great story about him and another famous mathematician, Harish Chandra, both of who ended up at the Institute for Advanced Study. They're both coming out of a lecture, a physics lecture, and Harish Chandra says, that physics is so messy, I have to become a mathematician, I can't stand it. And Dyson, who wanted to be a mathematician, said, physics is so gloriously messy, I must become a physicist. And so they swapped paths at that lecture and then reappeared as colleagues at the Institute years later. So Dyson, famous man at the Institute, there was visitor Harold Montgomery at the Institute. They have people who visit for a year from time to time. Dyson and Montgomery would see each other, mainly dropping off their kids at the nursery school there, but never really talked. And one day, Montgomery is giving a talk about his work on something called pair correlations, something about the zeta zeros. And he says, you have to talk to Freeman Dyson. Somebody wants to introduce him to Dyson. So they introduce him to Dyson, they start to talk about what they're working on. And what Montgomery's been trying to figure out is not exactly where the zeta zeros are, but how close or how far they are together generally, how they're correlated. And Dyson hears about Montgomery's story and he says, I can tell you how they're correlated. They go like the energy levels in an atom, I bet. And Dyson writes down some function, and Montgomery says, oh my God, that's the function. How could you know that? So this turns out, this generates this incredible, they would have found out eventually anyway. But basically speaking, so the dots there are some function that plot how pairs of zeta zeros are correlated. So basically saying, so the numbers get bigger at the end, saying that basically they're sort of far apart generally. They repel each other is what people say, and that that curved line there is some function having to do with the energy levels in an atom. Okay? So I don't want to belabor everybody's patience, so actually let me sort of summarize what's been going on for the last 20 years. And people have completely picked up on this fact that there's this deep connection between energy levels in atoms, energy levels having to do with quantum phenomena, quantum chaotic phenomena of all things, some interesting mixture of chaos and quantum mechanics. So chaos that occurs at a subatomic level, and that the connection between the energy levels that can occur there and the behavior of the zeros of the zeta function, at least numerically, is quite dramatic. People have computed this kind of thing for zeta zeros out to the power of like 10 to the 25th power. I mean, larger numbers than anybody could ever, larger than the age of the universe. And so this has generated an incredibly rich area of mathematics and connections between number theory and physics. And again, speaking, I don't have a PSA for this, but it does turn out now that trying to understand the patterns in the primes is fundamentally related to understanding the patterns that occur inside the atom. Things that are important if you're trying to build a quantum computer, things that are important if you're trying to engineer objects on the level of an atom. And, not that, some people are probably studying it for that reason, but, most people aren't. But presumably understanding the zeta function, I was talking to a physicist, Michael Berry, who's one of the most famous people working in this area, and he and mathematicians say that, the Riemann hypothesis is interesting, but if you could prove it and connect it, as people believe, to the atom, as they're trying to do, that's completely astounding, because it will mean all sorts of interesting number theoretic results, meaning things about physical phenomena. And in a funny way, that sort of brings one back exactly to where mathematics starts. Because, for the Greeks, numbers were all about our place in the universe. They were very mystical about them. And so it's a sort of, it almost has to be true somehow. So I think I'll leave it at that. So thanks for your attention.